In this video we will solve a problem on the torsion of a shaft here. Okay, so here again the shaft is a hollow type here. So what the data is given we'll read and we'll check one by one here. Okay, first I'll read the problem here. So a 2 meter long hollow cylinder shaft, it is a hollow type. So I'll draw first the hollow shaft here. Its length equal to 2 meter, that is data. Length of hollow shaft equal to 2 meter, that will be equal to 2 into 10 raised to 3 mm, right? Shaft has 2 meter long hollow shaft. Hollow cylinder shaft has 80 mm outer diameter. Outer diameter is, just I'll write the side view here. So outer diameter is 80 mm. This diameter, this is 80 mm. That will be equal to D naught. So D naught equal to 80 mm. Therefore R naught equal to how much? 40 mm. Its radius, outside radius is 40 mm. Outer diameter, and 10 mm wall thickness. Wall thickness is this one, right? This is 10 millimeter is given. So this thickness is given 10 mm. That will be equal to T, right? T equal to 10 mm. So from this, can we calculate the inside diameter and inside radius? That because the outside diameter is inside diameter plus 2 times thickness, right? We can use that equation here. So outside diameter equal to inside diameter di plus 2 times thickness, right? 2 times thickness. Outside diameter, how much is there? 80 equal to inside diameter plus 2 times thickness is, wall thickness is 10 millimeter. So this will be equal to di plus 20, 80. Therefore di equal to 70 millimeter, right? And 60 millimeter. 60 millimeter. This is the inside diameter. Ri is how much? Inside radius is 30 millimeter. We want this while calculation here. When the torsional load on the shaft is 6 kilonewton meter. What is 6 kilonewton meter here? It is the torque. Torque is given T equal to 6 kilonewton meter. 6 kilonewton meter. Okay. So convert this into Newton mm here. That is 6 into 10 raised to 6. 6 into 10 raised to 3, 10 raised to 3. 10 raised to 6 Newton mm torque. Determine the first one is maximum shear stress induced. We need to calculate the first one is maximum shear stress induced equal to how much? The second one angle of twist. Angle of twist theta. Theta equal to how much? Also draw the distribution of the shear stress on the wall of the shaft. We need to draw the distribution how much here, the inside, the total in this, the solid portion here, how much we need to draw the distribution of shear stress. Okay, take G equal to 80 GPa is given. G equal to 80 GPa. 80 GPa, convert that into MPa. 80 0.8 into 10 raised to 5. We can write here. That will be equal to 0.8 into 10 raised to 5 MPa. So this is the data is given, and we need to solve one by one. First we will go maximum shear stress. Maximum shear stress. So how we'll start here? Here torque we know, and the G we have Okay, length and everything we have. What is the equation? General equation for the torsion? We have one equation, T by Jp equal to tau by R equal to G theta by L. G theta by L. This is the general equation for the torsion. We derived in the previous video here. Now, which one we need to take to? This is a shear stress. We need to calculate. Shear stress we need to calculate. So we have here left side one equation, the right side one the equation here. Which one we need to take, this one or this one here? So G also we know, but theta we don't know. Theta we don't know. So if you take these two equations, two are unknowns. Here shear stress and the theta. So we cannot take this one. If you take these left side two equations, torque, we know the torque is given here, and we can calculate the polar moment of inertia, and we know the radius here. So take this equation. Take this equation and we will go there. Okay. So for outer radius, for outer, this is maximum at outside and the zero at the center here. Okay. So first for outside, take T. T is how much? The torsional moment is 6 into 10 raised to 6 divided by, what is the formula for polar moment of inertia? Pi d raised to 4 by 32. Pi d raised to 4 divided by 32 here. That is pi d is here d naught raised to 4 minus di raised to 4, right? D naught raised to 4 divided by di raised to 4 minus di raised to 4 divided by 32. This is polar moment of inertia, equal to, we want to calculate tau divided by R. R, which one we need to take, Ri or R naught? Because we are calculating for outside, here outside. For outside the diameter or for outside radius, we need to consider outside radius, that is R naught. R naught. Okay, R naught. Now substitute again this, if I simplify here, 6 into 10 raised to 6 divided by pi by 32 into di is, inside diameter is, we calculated already, 60 to the power of 4 minus outside is 80 to the power of 4 equal to tau divided by outside radius is 40. Okay, so simplify this and we will get the tau at R equal to 0, right? At R naught, tau equal to R naught. Better I will write this one at suffix R naught. Okay, it means here. So after simplification, we will get this value, that is 87.3 MPa. Okay, so now I will write the value 87.3 MPa here. Here this is the center. From here its value is, just note down this one as 87 point, how much I am getting here, 87.3 MPa at R naught. Now this is R naught. Now I need the shear stress at Ri, the inner radius at here. How much is there? That I need to calculate. So next step is, because in the last step he is given in the problem, you need to write the shear stress distribution on the wall thickness. Okay, so that's why we need to calculate the shear stress at the outside, shear stress at the Ri, the R equal to the inner radius. So same apply the second the same formula for the inner radius. What are the changes? The T, it doesn't change, and polar moment of inertia, it doesn't change, it will be same, but the tau is, it is inside, the shear stress is at the inner radius, and R is Ri we will get. Okay, therefore now I'll go for the second, for inside radius. What I'll get, this is same here, shear stress at Ri, okay, Ri, and this is Ri. So same here, that is 6 into 10 raised to 6 divided by Jp is the polar moment of inertia pi by 32, 60 to the power of 4 minus 80 to the power of 4. This is doesn't change, and here this at Ri, and what is the value here? The instead of the Ri, inner radius is how much? Inner radius is, inner diameter is 60, therefore inner radius is 30 millimeter. Substitute here 30 millimeter. 30 millimeter. So from this equation you calculate what is the shear stress at R inner radius, at R equal to inner radius. So after simplification we will get the value is 65.5 MPa. 65.5 MPa. This is the inner radius, the inner shear stress at R equal to I. Now I'll draw the same at radius I. Here inner radius hollow shaft 65.5. It is lesser than 87.3, right? So here it is lesser than 87.3 here. This is 65.5. So I am getting the shear stress distribution here. This is the center. This is the center. So this is the center. Here 65.5, and this is 87.3, and this is the 0. So this is the shear stress distribution in the right side. In the same way here also I am getting here in the downside. Here this is 87.3, and when R equal to Ri inside, this is 65.5. 65.5 MPa. So join here and here. So same we will get here. This is the stress distribution. Okay. In this wall thickness, now you can complete here. So here also you can complete. At R naught, the shear stress is 87.3. At Ri equal to 60, it is 65.5. First do that, then you can join that. From the center always it is 0 here. Okay. So now this is the first one is finished, shear stress. Now if you go to the second, angle of twist. How to calculate the angle of twist? What is the formula? Again, use the same general formula here. T by Jp equal to tau by R equal to G theta by L. Now in this case, T by Jp equal to tau by R equal to G theta by L. Now the second one is asking angle of twist. Angle of twist is here. So we need to use this one and this one. Either we can use this equation or we can also use this equation. Both, any two equations we can use here. Okay. So I am using the T by Jp, T by polar moment of inertia equal to G theta by L. G theta by L here. So torque we know that 6 into 10 raised to 3. The polar moment of inertia pi by 32 into d naught raised to 4. D naught is 80 minus di is 60. 60 to the power of 4, right? Equal to G is, what is the modulus of rigidity? 80 into 80 GPa, but I converted into MPa. 0.8 into 10 raised to 5 MPa divided into theta. Into theta divided by, what is the length here? Length of the shaft is 2 meter. That is 2 into 10 raised to 3. 2 into 10 raised to 3. So in this case only one is unknown. Theta is unknown. Therefore simplify and calculate theta. We will get angle of twist. We will get the 0.054. 0.054 radian. Convert this in terms of degrees. That will be equal to the 31 degree. That is 3.1 degree. 3.1 degree. This is the angle of twist. Okay, so we found the maximum shear stress induced outside of the wall and inside of the wall. Next, second one is angle of twist is 3.1 degree, and the stress distribution also we drawn here. Okay, so this is the solution for this problem here.